forcing function. So in this case, we will find out why that we don't really need to take care again about transient response, yeah, about switching function. So here, for example, if you have a linear electrical network means consisting of usually passive elements, uh, uh, resistive resistor, inductor, and capacitor. Then it is a voltage, a source, an independent source is connected to that linear electrical network. Okay, if the independent source here are sinusoidal, yeah, sinusoids of the same frequency, so they do not have variation in frequency, the same. Then for any variable in this linear circuit, any variable, current, voltage, whatever, the steady state response will be sinusoidal also, and of the same frequency as the independent source. Yeah, so this is one big law or characteristics that makes it easier for us to solve for any parameter, any variable inside this linear electrical network. So for example here, Vt, voltage T, we want to find It within this linear electrical network. Yeah. So if the independent sources connected to this are of the same frequency, then the steady state response, so here steady state response, and we are not speaking about transient response. Transient response takes time, and that's the topic of the previous chapter. But now when it is already steady state, what will be the amplitude, what will be the frequency, what will be the phase? So hence the Vt equals to A, for example, A sine omega t plus theta. This is the phase, this is the frequency, omega, A is the amplitude. Then ISS inside this linear electrical network will be equal to B sine omega t plus phi. Okay, so omega will still be the same. The frequency will be still the same throughout the whole system. What changes is only the B, the magnitude of the B, and the phase phi. Okay, why this is, I have to change back again to pointer. For example, here we have an inductive, yeah, RL circuit connected to Vt equals to Vm cosine omega t. This is an independent source and sinusoidal function also, but in cosine. Magnitude is Vm. What is It then? So using KVL and using the inductance law, so we obtain Vt here equals to RIT, voltage across the resistor, plus voltage across the inductance, which is L didt. Okay. So in steady state, yeah, the It will be equals to an amplitude A cosine omega t, the same frequency as the independent source, plus phi, the phase. Or we can express it as It equals to A1 cosine omega t plus A2 sine omega t. Okay, the phi here is expressed as A2 sine omega t. Cosine omega t plus, remember that cosine omega t plus phi equals to cosine omega t cosine phi minus sine omega t sine phi, right? So that minus term can becomes this A2. So didt will be equals then minus A1 omega sine omega t plus A2 cosine A2 omega cosine omega t. So dividing this by R, multiplying this by R to find this term, and multiplying this by L to get this term. So we will obtain, and rearranging this, regrouping again according to sine and omega, we will obtain minus L. So this will run from here, minus L omega A1 sine omega t. Then the other sine is here, R A2 sine omega t plus L omega 8 L omega A2, yeah, cosine omega t, plus RA1 cosine omega t equals to V. Vt here is Vm cosine omega t. So the cosine will be the same. The cosine term will be the same. So it means L omega A2 plus RA1 equals to Vm. The sine terms is the same. The sine term here on the right hand side of the equation is 0, right? So minus L omega A1 plus RA2 equals to 0. So from here, we get here. How do we obtain here? Let's try to calculate ourselves first, yeah, so that we are really sure. Here we can re-express. So this A1, yeah, we can multiply this by find A1, yeah, let's say by R, yeah, by R. And this one we can multiply by L omega. Okay, so we will obtain minus L minus R L omega A1 plus R square A2 equals to 0. So we change this one into A1 into the left side. R L omega A1 plus L omega square, right? A2 plus L omega Vm. Here equal, yeah, not plus, sorry. This equal. So then if we plus, this will cancel, right? Becomes 0. So this equals to R square plus L omega square A2 equals to L omega Vm. So A2 equals to L omega Vm divided by R square plus L omega square. Okay. Similarly, to solve for A1, yeah, then we multiply vice versa now. This will multiply by L negative L omega. Okay. Here negative L omega. Here we multiply with R. Okay, with R. So here we will obtain L omega square. L omega square A1 minus R L omega A2 equals to 0. Then R square A1 plus R L omega A2 equals to R Vm plus, so this will cancel, right? So we will obtain here L omega L square A1 L omega square plus R square A1 equals to R Vm, or A1 then equals to R Vm divided by R square plus L omega square. Let's see if our answer is correct. Let's erase first this. Yeah, sometimes you need to try yourself to derive the equation. In that case, then you will have more certainty. So A1 is here is correct. RVM divided by R square plus omega L square. A2 is this one. Omega here L VM divided by R square plus omega L square. So our answer is correct. Yeah. It is good if occasionally you try to derive the formula yourself so that you know where it is derived from. So determining the steady state solution can be accomplished with only algebraic tools. So remember here, you see here that the amplitude A1 and A2 is, yeah, we don't really care about sine and cosine here. We care, this is algebraic, simple algebra, substitution and elimination. Okay. So the solution is IT equals to A1 cosine omega t plus A2 sine omega t. The applied voltage is VT equals to VM cosine omega t. For comparison purpose, we can write then IT equals to A cosine omega t plus phi. So in this case, yeah, A1 equals to A cos omega cos phi, A2 equals minus A sine phi. So remember that this so this equal A cosine omega t cosine phi, right? Then minus ya, it is cosine identity sine omega t sine phi. Okay, so re-expressing again, so this becomes A cos phi cosine omega t minus A sin phi sin omega t. So this term become A1, this term becomes A2. Yeah, if we go to this solution. Yeah, A1 equals to A cosine phi, A2 equals to negative A sine phi. So from here, then we know A, yeah, is A square, yeah, A square, A1 square plus A2 square equal to A square cosine square phi plus A square sine square phi. So equals to square root. So A equals to square root of A1 square plus A2 square. Tangent phi equals to minus A2 divided by A1. Yeah, from here, from this expression. Then from the previous derivation in the previous slide, we will obtain A1 equals to RVM equals to RVM divided by R square plus omega L square. A2 equals to omega L VM divided by R square plus omega L square. So A from here, we substitute this into this equation, we obtain A. The amplitude A, yeah, equals to VM A square plus A2 square, square root of it, equals to VM divided by R square plus omega L square. The phi is arctangen of minus A2 divided by A1. This one divided by this one, omega L VM divided by R VM equals to omega L divided by R. Yeah. The IT then re-expressed in this form, IT equals to A cosine omega t plus phi. So IT equals to this VM divided by R square plus omega L square cosine omega t plus phi. The phi is this one. Yeah, arctangen, negative arctangen of, from here, tangen phi, negative arctangen of omega L divided by R. Okay, so then since L is not equal to 0, the inductor equal not 0, then it's not equal to 0, then the current always lags the voltage. Okay, here you see the voltage is Vm cosine omega t. The current has negative sign here of the phi. So it means that the current lags the voltage in inductive, resistive inductive circuit. If R equals to 0, yeah, if this is equal to 0, so the current lags the voltage by 90 degrees. So this, if this equal to 0, so this value becomes infinity, and the arctangen of infinity is at 90 degrees, right? So cosine, this becomes cosine omega t minus 90 degrees. The current lags the voltage by 90 degrees. So this is when the circuit is only inductive. Yeah, it contain only inductor, no resistor. Solving a simple one-loop circuit can be very laborious if one uses sinusoidal excitation. So if we use sinusoidal excitation like presented earlier, it's not that simple. Yeah? We have to solve for each of the term cosine, and we have to use all these trigonometric identities. To make analysis simpler, one relates the sinusoidal signal to complex number. Then the analysis of steady state will be converted to solving system of algebraic equation with complex variable. So we try now to re-express the signal which is originally in sinusoidal or cosinusoidal form into exponential form, into complex numbers, using Euler identity. Exponent j theta equals to cosine theta plus j sin theta. Okay, remember this is from I think you will learn in engineering mathematics, but you learn also in calculus. Yeah. So Vt here equals to Vm cosine omega t. The Yt will be equals to A cosine omega t plus phi. Yeah. The same cosine, the same frequency, but now with additional phase phi. The magnitude will also change from Vm into A. If Vt is expressed as Vm sin omega t, Yt will be equal to A sine omega t plus phi. If we multiply it by j and then ending this and this, so this will be j a sine omega t plus phi. We add 2yt equals to a cosine omega t plus phi plus j a sin omega t. Okay. So Vm here also Vm exponent j omega t. Yeah, here will be adding. So will be Vm cosine omega t plus Vmj sin omega t. So it becomes Vm exponent j omega t. Well, this part becomes a exponent j omega t plus phi. Yeah, this part a exponent j omega t plus phi, and we know that this equals to a times exponent j omega t multiplied to exponent j omega t, exponent j theta, yeah, j theta, sorry, multiplied to exponent j omega t. Then since the frequency is the same here, omega the same, this is the same, then we can skip the term exponent j omega t. What matters now is the new amplitude A and the introduce phase lagging or phase leading theta. Yeah, from Vm, so we eliminate exponent j omega t, yeah, from all these terms. Yeah, divided by exponent j omega t becomes Vm. This divided by exponent j omega t becomes just A times exponent j theta. So the simplified form will be the function maps the independent voltage source here Vm, just expressed as magnitude because we know the frequency is the same, becomes A exponent j theta, becomes a new magnitude with an introduced phase lagging or phase leading. Okay. So this is the relationship between complex to polar. Remember from high school mathematics or also from calculus. X plus j y in the complex field equals to the the radius times exponent j theta, while r equals to the square root of x squared plus y squared, and theta here is arctangen of y divided by x. So this is actually y. This is y divided by x, arctangen y divided by x. Correct? Please correct me if I'm wrong. So this is actually y divided by x, the arctangen. So x equals to r cosine theta, y equals to r sin theta. So then if from going back to the previous problem in the previous slide, Vt is expressed as Vm exponent j omega t, assuming that the current inside the electrical circuit network is Im with magnitude Im times exponent j omega t plus an introduced phase phi, yeah, using KVL. Yeah, so this is still the same problem, the RL circuit. L di dt plus RIT equals to Vt. So the IDT from here equals to j omega Im exponent j omega t plus phi. So this basically equals to j omega I. So L di dt plus RIT equals to j omega L Im exponent j omega t plus phi plus R. Where is I? This one, Im exponent j omega t plus phi. So then we group, based on since this is the same, exponent j omega t plus phi, it's become j omega L plus R multiplied to Im exponent j omega t plus phi. Or then we can re-express this one as j omega L plus R Im exponent j phi multiplied to exponent j omega t. This is the same. This is also the same with has exponent j omega t. J omega L plus R multiplied to Im exponent j phi exponent j omega t equals to Vm exponent j omega t. Since frequency doesn't change in the voltage source and the corresponding current source in the linear electric network, so this factor can cancel each other. So Im exponent j phi equals to Vm divided by j omega L plus R. Okay. If we then multiply it, this with 1, and 1 is expressed as R minus j omega L divided by I minus j omega L. So this becomes Im exponent j phi equals to Vm multiplied to R minus j omega L divided by R square j multiplied by j is minus 1, and minus plus. The times minus is positive omega L square. So now the denominator is in real number. No, it doesn't contain any imaginary component, only the nominator part. So R minus j omega L equals to the square root. This is the R equal to R square plus omega L square exponent minus tan minus arctangen. This is the phase omega L divided by R. Okay, omega L divided by R. So this is the what in the imaginary in the complex plane represents the x and y component. Okay, so this is the magnitude of this. So this is re-expressed in terms of this is this is x plus jy. This is re-expressed as r exponent the phase. The phase phi equals to arctangen of omega L divided by R. The radius or the magnitude is the square root of this square R square plus omega L squared. Okay, from Euler's identity. So using this, then we can re-express again. I am exponent j phi here, Pm multiplied by R minus j omega L, which is this one. Is this one divided by this. So the denominator becomes square root of R squared plus omega L squared. Okay. So Im equals to, from here, from this expression, we know that this, let me change to pen again, this corresponding to this value, well, this one corresponding to this value. Okay, so Im equals to Vm divided by square root of R squared plus omega L squared, and the phi here equals to minus, minus arctangen of omega L divided by R. Okay. So Vt, coming back here, is Vm cosine omega t. Basically, is the real form of Vm exponent j omega t, because the imaginary part is not taken, so we only put the real part. It here, yeah, it equals to the real part of Im exponent j omega t plus phi minus phi equals to Im cosine omega t minus phi. Okay, so this is the circuit. Okay, I think for today I will stop until this point, yeah, where we until expressing sinusoidal as complex as complex number, and later on next session, next subsection, we will try to introduce phasor concept, and where what matters is only the amplitude and the phase, because frequency is considered the same, but we will draw it as a phasor. Okay, are there any questions so far?